Hello students, this is Dr. Ben. I'd like to take some time to work on a problem that has to do with the material out of Chapter 5 on circular motion dynamics. And here we have a situation dealing with a Ferris wheel and a person riding in the Ferris wheel. And so we know that a Ferris wheel is oriented in the vertical direction. Vertical circular motion. And let's go ahead and read the problem and make a list of what we know and what we want to find, and then we'll go ahead and draw a picture and try to make some progress on this. So a person is given with a mass of 60 kilograms. The Ferris wheel has a radius of 16 meters. When at the top, the seat exerts a 540 Newton force on the rider. So that would be what we would call a normal force, and I'm going to label that at the top. That's going to have a value of 540 newtons. And then the acceleration due to gravity will set to be on 10, the approximate value. Alright, and so what we want to find in this problem, in part A, it says find the speed of the person. So that's going to be the rotational velocity of the point on the edge of the Ferris wheel. And then in the second part of the problem, we want to find the force that the seat exerts on the person at the bottom, and that's what we would call the normal force at the bottom of the path. Alright, so let's go ahead and make a sketch of a part of the path of the person around the top of the trajectory. So there's the top of the motion. We'll put the person sitting in the seat up at the top. Alright, so let's draw a force diagram for this situation. So the person is attracted to the earth through the force of gravity, but the seat is below the person, so the normal force exerted by the seat on the person at the top points upwards. The center of the circle is below our observation point, and so the acceleration in the circular acceleration points downwards, and we can just pretend that the Ferris wheel rotates counterclockwise. Alright, and so we need to use Newton's second law and some of the circular motion kinematics in order to solve this problem. So the first thing that we want to do is to find the velocity v. Alright, so let's go ahead and write down Newton's second law, and that will account for the forces that act, and then we'll see what we need to do with the kinematics. So we'll say that the acceleration is equal to the net force on the person divided by the mass, and we'll apply this at the top of the motion as our picture shows. So I'll say that A sub c equals the net force, which will be N at the top minus the weight divided by the mass. And since in the first part we want to find the value of the speed of the person, actually the speed of the Ferris wheel, a point on the edge of it, I want to use the formula for the centripetal acceleration, that is the v squared over r, because that is useful to find the velocity, and we know all the other numbers. So I'll go ahead and substitute that in. I get n at the top minus mg divided by m, and I just have to do a little bit of algebra to isolate the v by itself. So I would have r times n at the top minus mg divided by m, and if we take the square root of both sides, then I would end up with v is going to be equal to the square root of r times n top minus mg divided by m. Alright, so we'll get our calculator out and figure out this number. The radius is 16. The normal force at the top was 540 newtons minus the mass that was 60 times g of 10. Close my brackets, and then divide by that 60 again. Alright, so if I get my calculator out, I'll take $540 minus 6 times 10, so that's minus 600. So that's going to equal negative 60 times 16, and then that's divided by 60. Alright, so that gives me the square root of negative 0.266, and I'm really concerned by that minus sign because I know from math class that I can't take the square root of negative numbers. So I want to go back to my diagram just for a second and see what is up here, why that answer turned out to be negative. And now when I look back, I realize that I should have reversed the signs on the directions of the two forces, because I should have referenced it to the positive direction pointing inwards, and I referenced them to the positive direction pointing outwards. So actually that minus sign should not be there, and if I get rid of that minus sign then and take the square root of my answer, I get 0.52. So the velocity at the top would be 0.52 meters per second. Okay, let's check that one last time without the minus signs. So we have 600, which is 60 times 10, minus 540, times 16, divided by 60, square root, and this time I got 4. So I must have made a mistake on my calculator before, so I'm going to change that to 4.0 meters per second. Alright, so I think we got that part. So that's going to be the uniform speed that this Ferris wheel has as it goes around. Alright, so now we can focus on the bottom of the motion of the Ferris wheel around its orbit. So if I sketch the situation at the bottom, so I have part of a circle, and we can let the object be located there at the bottom. So now I want to draw my force diagram, and the weight should point down, and the normal force at the bottom should point upwards towards the center, and the acceleration points in that direction also. Alright, so again, I can apply Newton's second law just like I did at the top. I would say that A equals the net force divided by the mass. I'll apply this to the person at the bottom of the orbit. So I'll have A sub c is now going to equal n bottom minus mg divided by n, mass. The acceleration will be v squared over r. And now I want to solve for n bottom. I have to do a few steps of algebra. So let's go ahead and move our paper up, and we can do that. So we'll cross multiply. mv squared over r is going to equal n bottom minus mg. So I take the mg to the other side and make it positive. So therefore n bottom is going to equal mv squared over r plus mg. Alright, so we can plug in the numbers that we know. So we have the mass of 60 kilograms. In the first part, the velocity, the speed was equal to 4, so we have 4 squared divided by the radius, that was 16, and then plus 10 multiplied by g. Alright, so we have 4 squared, which is 16, divided by 16, which is 1. So we have 60 times 1 plus 10 times, oops, it's not 10, it's the mass is 60, plus 60 times 10. So we have 60 plus 600, which is equal to 660 newtons. I'll try this. 660 newtons. So the tension, the normal force that the seat exerts on the person at the bottom is larger than the normal force that the seat exerts at the top. It was 540 newtons at the top and it's 660 newtons at the bottom. Alright, so I'll just double check that I have my units and my significant figures. And we have this problem completed.